So today we're going to continue learning about how we describe acids, acid strength, that kind of thing. So it's kind of a starter activity. I want you to just go ahead and pause after I give you the instructions. And let's say that this end of the scale is acidic and this end of the scale is basic. Okay, and I'd just like you to throw in some values of concentration of H3O plus in an acidic solution, a neutral solution, and a basic solution. Okay, well hopefully you remember that for a neutral solution, concentration of H3O plus is 1 times 10 to the minus 7. Okay, and then we have this equation Kw equals concentration of H3O plus times concentration of OH minus. So, and we know that this value is always 1 times 10 to the minus 14. Okay, so at its most basic, if you really don't have any of this, you'd have basically all hydroxide. Okay. So at this point, your concentration of H3O plus is going to be 1 times 10 to the minus 14. Now you could go less than that. All right, you could go less than that, but I'm picking that number for a reason. And the counter to that is, well, the highest I could go would be 1, because if I make this 1, this would be 1 times 10 to the minus 14. So what I did over here was I said this was 1 molar, and I made that 1 times 10 to the minus 14. So this is concentration H3O plus. Okay. All right. So now I could also use this, and I could fill in some values of concentration of hydroxide ion. Okay. Would you pause here? See if you can figure out these values. Well, if concentration of H3O plus is 1, then concentration of hydroxide is 1 times 10 to the minus 14. 1 times 10 to the minus 7, and 1. Okay. So when I look at these numbers, I kind of think to myself, wow, those are annoyingly small. All right? Nobody really wants to be working in the 10 to the minus 7 to 10 to the minus 14 range in values. That just doesn't sound like a good idea. So we actually use log scales to make this more bearable. And a lot of you have had logs before, and so I'm just going to give a quick overview of how logs work and what we're going to be using them for. Okay, so if I have some value b to the y equals x. Okay, so I could write these as 2 to the 0 equals 1, 2 to the 1 equals 2, 2 to the 2 equals 4, 2 to the 3 equals 8, and 2 to the 4 equals 16. All right, now I could keep going with that. So this b that's the base. Okay, this number y is the power to which the base is raised, and x is just the number that comes out. All right, now what logs do is logs do something like this, where you say the log of b of x, so log b, so the base, log base of x, equals y. Okay, so what this does is logs basically just tell you how many times the base has to be multiplied by itself to get this value x. Okay, so in 2 to the 0, log 2 equals log 2 of 1, okay, so x value is 1. Log base 2 of 1 is going to be 0. Log base 2 of 2 is going to be 1. Log base 2 of 4 is going to be 2. log base 2 of 8 is going to be 3, and so on and so on and so on. So the last one I need to do in this series is log base 2 of 16 equals 4. Okay, so the log just tells you how many times you have to multiply the base by itself to get this value x. Okay, so we're not going to use a lot of log base 2 because that's kind of a funny scale. But what we do is we use a lot of log base 10. Okay, so log base 10. And this log base 10 is sometimes called common log. And oftentimes this 10 here is just omitted. So when you find this on your calculator, it's just going to be log. Okay, so let's take a quick look on that. Okay, so your calculator will hopefully look something like this. You'll see over here you have a log value. Okay, log value. I'm just going to clear everything. So here's my log. Okay, so if I wanted to do, let's say, well, let's do this kind of scale with logs. Okay, so log base 10 of 100 is going to be what? Well, it's going to be 2. Okay, so 10 times 10 is 100, so 10 squared is 100. Log base 10 of 1,000 is 3. So you could see that using this log base 10 scale, okay, instead of going up from 100 to 1,000 in a graph, I could just go up 2 to 3 in a graph, which would make my numbers much more reasonable. Now the great thing is, this also works very well with scientific notation, all right? Let's say that I have log base 10, which I'm just going to start leaving off, of 1.0 times 10 to the 4th. Okay, well, how many times does 10 need to be multiplied by itself to get this 1 times 10 to the 4th? The answer is pretty clearly 4. Okay, what about log base 10 of 1.0 times 10 to the minus 7? Okay, now I'm picking this number for a reason. This would be minus 7. And log of 1.0 times 10 to the minus 14. That's just going to be minus 14. Okay, now how would I put these in on the calculators? Well, let's take a look at this one. Okay, so on your calculator, you push the log button first. Okay, now notice it starts a parentheses for you. And I'm going to do 1e negative 7. Okay, and when I hit enter, negative 7, E0, so negative 7. Now, what happens if I do this? Log 1e minus 7. Okay, it does not recognize this, the negative, the subtraction symbol, as a negative. So you need to make sure that you put the negative in there as the negative, all right? So if you get a syntax error, that's probably where you messed up, all right? Now, what about something, how about, most of the time we won't be using like nice round numbers like this, right? So what about something like log base 10 of 726. Okay, well, you're going to be able to use your calculator for this, all right? Now, I know that it's between 100 and 1,000, which means that the value is going to be somewhere between 2 and 3, probably closer to 3, right? So let's plug it into our calculator. Okay, log of 1, or sorry, I said 726, right? Log of 726. Okay, close parentheses, that's what we're looking for. Okay, 2.8. So it's between 2 and 3, closer to 3. Okay? So a log scale basically just compresses values, right? Rather, like I said here, rather than going from 100 to 1,000 in a graph, you would go from 2 to 3. Okay? And the log scale that we're going to use a lot in acids and bases is the pH scale. Okay? pH scale. And the pH scale is just a log scale that measures the concentration of hydronium. All right. Now, pH, nobody really knows what it means, but probably power of hydrogen. So like how much hydrogen ion you have in your solution. Okay. And the equation for pH is log of concentration of H3O+. All right? So I could also do POH is log concentration of OH minus. Now, I'm going to make one small change here. All right? For a neutral solution, I know the concentration of H2O plus is 1.0 times 10 to the minus 7. Well, I already know that the log of 1.0 times 10 to the minus 7 is negative 7. And since we're already kind of making a shortcut here, and let's try to be even lazier, let's just say, hey, I don't really like negative numbers. I'm a positive kind of person. I like positive values. Well, the pH equation is actually the negative log of H3O plus, and POH would be the negative log of concentration of OH minus. Okay? So let's go back up to our scale here. At neutral, the pH of this solution is going to be the negative log of 1 times 10 to the minus 7. So that's just 7. Okay? Here it's going to be negative log of 1, which is just going to be 0. And here it's going to be negative log of 1 times 10 to the minus 14, which is going to be 14. Okay? And when you learned your pH scale in middle school, you probably learned a scale that was from 0 to 14. All right? Well, what about POH? Well, POH is the negative log of concentration of hydroxide ion. So here it's 14, right? Here it's 7, and here it's 0. So you can see that these scales are kind of redundant, okay? Yeah, you can see that these scales are kind of redundant. Now, sometimes I might be given a pH and ask for a concentration of H3O plus, right? Well, if my log base 10 of 100 equals 2, and I know that 10 to the 2 equals 100, okay? So if I'm given a log of some value and I really want the value itself, okay, what I really need to do is I need to raise both powers to the base. So if I do what's called the anti-log, okay, which is really just raising both sides to the base, the power of the base. Well, in this case, that's 10. So I do 10 on both sides, okay? And 10 to the 2 is 100. All right? So this would just simplify, or sorry, what I kind of mean to say here. So if I have my equation for pH equals negative log concentration of H3O plus, all right, I want to isolate H3O plus by itself. Okay, so the first thing that I'm going to do is I want to get rid of this negative sign. So I'm going to multiply both sides by -1. Okay, and then I'm going to take the anti-log of both sides, which means I'm going to raise it to the power of the base, which this is common log, so that's just 10. So 10 to the minus pH equals 10 to the log of H3O plus. The log and the 10 to cancel out, and what I get is just the H3O plus. Okay? I can do the same thing with POH and get concentration of hydroxide ion. And if only, oh, if only, I had put all these equations somewhere handy, like, I don't know, on an equation sheet. Well, here's the equation sheet that you've been given for this class. pH equals negative log H3O plus, POH equals negative log OH minus, pH plus POH equals 14, H3O plus is 10 to the minus pH, OH minus is 10 to the minus POH, OH times H3O plus is KW. All right, you have all the equations that you need. All right, I'm really not asking you to memorize a lot of stuff. It's really all about application, okay? And this section is actually fairly straightforward. It's not till I start giving word problems where pH is just part of the problem that this starts to get a little complicated, okay? Now, one of the things that I think might be helpful, okay, is I kind of came up with this little square. Sure, it could be a circle, whatever, I don't know. And let's say that I have pH on this side and POH on this side, and I have concentration of H3O plus on this side and concentration of OH minus on this side. Now, this is cool because I know the relationships between each of these things. So if I'm going from H3O plus to pH, that's pH equals negative log concentration of H3O plus, and going the other way, H3O plus, concentration of H3O plus equals 10 to the minus pH. pH plus POH equals 14. That would be the relationship on the top side. And then this is the log, anti-log again. And then this bottom is just H3O plus times concentration of hydroxide ion equals KW. All right, so you know how to move around this thing. But oftentimes I'll give you like a pH and ask for an OH minus. So you have to work your way around the square, however you choose, and that does mean that there's more than one right way to do these problems. Okay, so that's just something to keep in mind as we work through this. All right? So here are some pHs for some common materials. Notice this side is kind of more acidic. Okay, let's say that these are kind of the more neutrally type things, and these are more basic. Okay, yeah, I mean, gastric juices is basically just very concentrated hydrochloric acid, lemons, vinegars, soft drinks. Now this is really interesting. Soft drinks have, if you look on your next bottle of Diet Coke or Pepsi or whatever it is that you drink, you'll see phosphoric acid on the label, okay? And one of the reasons is carbonic acid forms an equilibrium with water and carbon dioxide, okay? So one of the ways that soft drink companies will increase carbonation is they'll bottle under pressure, which we've talked about before, okay? And they'll also add an acid, okay, to kind of keep this solution acidic so that CO2 can pick up protons and move backwards and make more carbonic acid, okay? All right, so what is the pH of a neutral solution? You should be able to answer all these questions pretty easily. pH of a solution is 7. POH of a natural solution is 7. And then the last one that I wanted to show you, and I've kind of already alluded to it, is pH plus POH. Okay, Well, for a neutral solution, that has to equal 14. And if I look back at my chart that I made up, okay, it actually always equals 14 because as one goes up, the other one goes down. So that's pretty cool. And addition subtraction is nice and easy. And notice that this functionally comes out of this equation. Okay? Because if I'm looking at just the exponents here, this is -7, this is -7, and this is -14. And when you multiply things that have exponents, you add the exponents. All right? You should know that by now. So these two are very, very closely related. All right? All right. So I'm gonna do a couple samples before I turn you loose. These are kind of varying degrees of difficulty. Determine the pH of a 1 × 10⁻⁴ molar solution of HBr. All right, well, I'm doing pH. Okay, so if I do my little pH, POH, concentration of H3O+, concentration of OH-. All right, I know that I can go straight from H3O+ to pH, all right? Which means I'm going to use pH equals -log concentration of H3O+. All right, well, that's great, but I don't actually have the concentration of H3O+. Well, this is an acid, right? You can identify it because it has a proton on the front. So HBr plus H2O yields H3O+ plus Br-. Okay, there's my hydronium ion. Now, at this point in the year, I'm pretty comfortable with you saying concentration of HBr is equal to the concentration of H3O+, as long as this reaction kind of goes to completion. All right, I could also set up my dimensional analysis, but this time I'm looking for a conversion factor. So this is one of those rare times when you're going to start with a conversion factor. HBr, or 1 liter solution. Okay, now I'm going to assume that the volumes are the same. So really all I'm doing now is a 1 mole H3O plus, 1 mole HBr. Okay, so either one of these methods will work. Okay, go with the one that you're kind of more comfortable with, because you need to be able to do these quite easily and quite quickly. All right, so this is -log of 1 × 10⁻⁴. Okay, so my concentration of HBr is also equal to my concentration of H3O+, and this just gives me a value of 4.0. Okay. Determine the POH of a solution of 5 × 10⁻⁴ solution of calcium hydroxide. Okay, then determine the pH of this solution. Well, again, okay, this is POH. So POH, I'm probably going to need this hydroxide ion solution. Okay, so the first thing that I'm going to do is I'm going to write my equation. Okay, now this is a metal hydroxide, so remember with metal hydroxides we just write the dissociation reaction so we don't get too confused. All right, now the important thing to keep in mind in here is 2 times the concentration of calcium hydroxide equals the concentration of hydroxide. Okay, you could also prove this to yourself in a mole to mole ratio if you need to. All right, and so what I can do is POH equals -log concentration of OH-. Okay, so that's -log of 2 times this, which is 1.0 times 10⁻�3. So this is, 2 times 5 times 10⁻⁴ is concentration of hydroxide. So that's 1.0 times 10⁻�3 is your concentration of hydroxide. Okay? All right, and -log of 1 times 10⁻�3 is 3.0. Nice and easy. I haven't even had to use my calculator yet. Oh, now this problem also asked me to determine the pH of this solution. Okay, so I'm going to need a little bit more room here. Now, I could, if I wanted to, go from concentration of hydroxide to H3O+ to pH, or I'm at POH right now. I can just use the POH plus pH equals 14 to get to this last place. Okay. Now, a lot of you are going to be going on to take physics, and physics has a lot of equations. Okay. And one of the things that physics students tend to do is they tend to get equations kind of flipped in their head and mixed up in their head. Okay? It's very important to write the equation down in its unaltered form. Then solve for what you're trying, isolate the variable you're trying to solve for. All right, so in this case, I'm trying to find the pH. So pH equals 14 minus POH, which is 14 minus 3, which is 11. Okay? There you go. So the next one that I'm going to do is this one. The pH of a solution is 10.0. What is the concentration of hydroxide ions in the solution? Okay. So this one's a backwards one, right? So here's my square. Concentration of hydroxide. Now, I'm trying to go from pH to concentration of hydroxide. So I like to go this top route because I like this conversion right here. All right. So pH plus POH equals 14. So POH is 14 minus pH, which is 14 minus 10, which is 4. Okay. Now, from here to here, I'm going to use concentration of hydroxide ion is 10 to the minus POH. Okay. So this is 10 to the minus 4. That's my POH, which is 1.0 times 10 to the minus 4. Okay. All right. So there's my concentration of hydroxide ion. Now, the second part is, if the solution is this, is strontium hydroxide, what is its concentration? All right, well, strontium hydroxide is just a metal hydroxide, so it dissociates into strontium ion plus 2 hydroxide ions. So I know that concentration of strontium hydroxide 2 times the concentration of strontium hydroxide equals the concentration of hydroxide. Okay, make sure that you don't put this on the wrong side. Okay, that's big no-nos. So concentration of hydroxide ion, or no, sorry, concentration of strontium hydroxide equals concentration of hydroxide ion over 2, which is 1.0 times 10 to the minus 4th divided by 2. So that's going to be 0.5 times 10 to the minus 4, which is 5.0 times 10 to the minus 5. Okay. So this has to get bigger, which means this has to get smaller, so that's 10 to the minus 5. Okay? So there are some sample problems. This third one is really about as tough as I can make it today. I might be able to add on some stoichiometry at the end, like I've done here, but that's about it. So good luck, and I'll see you tomorrow.